Hello, folks. So my name is Paul Hudson, and my talk today is called Special Effects with SwiftUI Text. And I want you to cast your minds back to the early days of computing, also known as 1991, when back then Microsoft had just launched something very new and very important, their very first Office suite for Windows. And it was so old at the time, so brand new as an idea, it was even called the Microsoft Office. And their slogan, believe it or not, was Microsoft making it all make sense. And one of the ideas they had to make it all make sense was a thing they called word art. And word art let regular users add text effects in Word documents. They could warp text, they could add colors, they could add gradients and more. And in the 90s, and let's say early 2000s, this was considered to be very cool indeed. And to be fair, it existed alongside things like GeoCities, where websites like this were very, very normal. They could basically make your eyes bleed. Now, some people might look at this with nostalgia and miss those early days. But if you haven't seen it before, if you're very, very new, the key rule is this. If your text was easy to read, you weren't trying hard enough. And word art let you take a boring document like this and transform it into an ugly, boring document like this. And so folks loved it. Now, these days, you don't see word art and similar design so much anymore. It's a distant memory. But here, at TriSwift Tokyo 2025, I want to say I miss that word art style. And so the actual title of my talk is this: Word art is back, and SwiftUI is to blame. We're going to see how much of word art we can reasonably reproduce in one short talk. So, along the way, I hope you'll be left with some inspiration. I hope you'll be left with some understanding of what SwiftUI can do. And hopefully also you'll be left with only a little bit of eye damage. We're going to find out. I should say, though, there's going to be a lot of text in this video here, so please don't try and follow along live. You'll just hurt yourselves. All the code's available at the end. OK, let's start real simple. Here is a basic piece of SwiftUI text with some markdown styling attached to it. I'll give this thing a nice chunky font size, so you can see even in the peanut gallery at the back, and a nice big line spacing as well. Again, making it easy to read. And here's the result. Obviously, massive round of applause, folks. Come on. I'm kidding. Look, this is live text, right? Which means as the window resizes, it'll reflow naturally in that area. But the question is, how does it become that way? How does our SwiftUI code get put into pixels on the screen? Well, behind the scenes, this gets broken down to three things. We have lines, we have runs, and we have glyphs. Let's look at what each of those actually mean. Here's our lines. A line is a simple line of text you can see on the screen. But again, as the window resizes, it'll wrap into more lines or fewer lines as necessary. Inside lines are runs. You can see them here in green. A run's a single chunk of text inside a line with the same formatting. You can see here the word important is its own run because it has bold italic styling attached to it. And then inside runs, we have glyphs, individual letters, here in blue. As you can see, every letter, including every space, is a glyph. Now, these lines, runs, and glyphs all coexist at the same time. And now, from iOS 18 onwards, SwiftUI gives them to us to render however we want to. You have complete control over how every single letter is rendered if needed. And again, this is all live text, so we can control the way it's being redrawn. And it's all happening through a protocol called TextRenderer. This allows us to add a custom render of our own choosing, custom styling, and attach it to any text we want to be rendered in the custom style. Let's try it now with a simple example renderer called striped renderer. Now, conforming to the protocol means adding a single method called draw, which will handle all your text drawing for you. Inside there, you'll be given the text layout to render, along with the graphics context to draw that text into. And then it's up to us to do with that text whatever we want to in that graphics context. We can draw it however we want. Now, earlier, I said that text layouts are made up of lines. And this thing's actually a sequence. So we can loop over it. So in our drawing code here, we're going to loop over all our lines and also read the index in the sequence. Then, if our index is an even number, we'll reduce the drawing opacity down to 0.35. So it's mostly transparent. Otherwise, we'll leave it at full opacity. And then draw our line of text. And that's our initial text renderer done. It's nothing complex. Back in our view code, we need to add one line here. The text renderer modifier. It'll attach our striped renderer to our text. And here's the result. Not doing a lot, I know, but you can see straight away we've rendered alternate lines in a lower opacity. And again, this remains live text, so it'll reflow and be read out by things like VoiceOver and more. Now, I want to focus on just two parts of this code here. First, context.opacity. That's how we adjust the opacity of our drawing context. And that's provided to us for all rendering of this text. Any changes you make to this context will affect the whole rest of this drawing pass. So be careful. Second, we use context.draw with a line to draw a line of text. You can also draw a single run in a line or even a single glyph inside a run, all the same context.draw call. And this text render protocol gives us these lines in a really clean way. Here's all the lines. Then here's all the runs. Then here are all the glyphs. And we can use context.draw on any of those to draw individual lines, runs, or glyphs as needed. And both lines and runs are sequences, so we can loop over them. Even better, we can subdivide our text into our own values, creating our own runs with custom attributes. As an example, we could define a new attribute to handle text highlighting like this. It's an empty struct, but it conforms to this text attribute protocol. And it doesn't actually do anything to highlight. It just allows us to mark a piece of text as being highlightable. When it comes to using it, here's our code from earlier. We're going to add before it the word important as a separate text view. And then attach our custom attribute to that important text. Finally, we'll use string interpolation to place that highlighted text inside our other text. Again, this does not do anything to highlight text. We're just marking some content with a custom attribute. Changing the way it looks on screen is always handled by whatever type conforms to TextRenderer. In this case, we can make a new highlight renderer that tracks a highlight color. Then, when it comes to drawing our highlight, we'll loop over all our lines, then all the runs in each line, and check whether that run has our highlight attribute set. If it does, we draw the highlight. Regardless, we draw the text. Now, of course, the real question here is, how do we draw the highlight? Well, every line, every run, and every glyph provides to us a typographic bounds property, describing its size, its location, and more. So we could read that value for the current run, which is where our highlight attribute is. Then use that to make a rectangle path and fill that with our highlighting color. And that's all the code. We get this effect. Only the parts of the string we ask for get highlighted. Plus, we can customize the highlight color just by changing a single value. So we've seen how to modify lines with our zebra stripes and how to modify runs with highlighting. Let's go further. Let's go down into runs and modify each glyph, each letter in a run individually. As an example, we can make a new wave renderer. So we push letters up and down by some amount. How much will be controlled through strength and frequency values to make it customizable. So we want to add properties to track those two values. We'll then change our TextRenderer modifier so we pass in values for those things. I'll use 20 and 0.5 just to get us started. When it comes to rendering our text this time, we're going to apply the strength and frequency to create an effect on individual letters. This means looping over all our lines, then all the runs in each line, and then all the glyphs in each run. We're reading the glyph's position in this run at the same time, so we know how far through the run it is. And then inside that triply nested loop, we'll draw the current glyph. To render glyphs, we'll start by calculating a y offset for every letter based on its position in the run. Using the sine function here will give us a nice smooth wave effect. And now we'll get a copy of our context for drawing, because remember, any changes you make to that graphics context will affect the rest of this drawing pass. And we don't want every letter to move by the same amount, just this one. So we get a copy of it, so we can modify only the copy. We can then move drawing just for the copy, and then draw the current glyph at that new offset. So SwiftUI's graphics context is a value type, so we can make changes to copies without affecting the rest of our drawing. And now we get our text drawn like this. This already gets us one of the classic word art styles. So to complete the look, we just have to add a nice bright gradient to the text, like that. Very nice. We can do better. We could make the offset amount a local piece of state in our content view, like this. Now we'd use that to create our text renderer. And that's neat, because it's now customizable. But it's also neat because we can ask SwiftUI to animate this value for us, to allow us to move between wave strengths dynamically. This takes just 2 steps. First, you want to add a new property in our text renderer to tell SwiftUI what to do with animatable values. In our case, we want SwiftUI to automatically apply any animating changes to our strength property. Now we can go back to our view body and add an onAppear modifier. It will start an animation that will repeat forever. And that animation will set our value offset to 20. So it'll move between -20 and +20 forever. And now get this effect. Really, all we have to do here is change the text to be something like under construction, and we're back to 90s straight away. And we're going to use the exact same technique to create a whole bunch of other movement-based effects. For example, rather than using a smooth sine wave like this, we can instead choose completely random numbers. If we then modulate the range of that random number, we get a simple earthquake effect. So, rather than using a sine wave in our code, we'll instead pass in a movement amount and randomize inside that range. A tiny change. And now we get this. Let us jump around, mimicking a shockwave. For extra fun, we can even apply a gentle blur to the graphics context based on the current movement amount, increasing the shaking effect. So now, when they're shaking more, they're blurred more too. So you've now seen how you can adjust lines of text, runs of text, or individual glyphs inside runs. We've looked at custom attributes, and now we've just seen animations too. And the result so far is interesting. But if you want to go to the next step towards word art, we need to go further. You see, with a simple text renderer here, we have some control over how things are rendered. But we can't do more complex effects. We can't, for example, do things like this perspective tilt or the curved text below. For those, we need another technology that's very dear to my heart: Metal. Metal has been a tight fit with SwiftUI since iOS 17. We can literally send SwiftUI views off to Metal for adjustment, writing code that can recolor things or warp their shapes and more. Metal lets us do things that simple graphics filters cannot. If you imagine this picture here being broken down into all its individual pixels, SwiftUI lets us run every one of those pixels individually through Metal, transforming them however we want. And that might sound really, really slow, but in practice, it's screamingly fast, because the work can be split up perfectly. The job of handling one pixel does not depend on handling another pixel, for example. They're done at the same time. Which is why a modern CPU has thousands of tiny compute units designed to run one of these shaders at a time. So it's really, really fast. However, there is one speed bump. Metal code is not written in Swift. Instead, it's written in Metal shading language. But it's a C-like language, so hopefully it's OK for most folks to read. Now, if you want to learn more about Metal, awesome. I have a whole Metal shader repository on GitHub called Inferno, open source, full of great shaded SwiftUI. But let's take a look at rebuilding this perspective tilt effect in word art. Here's some Metal code for you. We'll start with just the function signature. This stitchable part here means Metal can combine this shader with other shaders it runs as part of a larger SwiftUI rendering pipeline. It'll return a float2, which contains x and y coordinates. We have to tell SwiftUI where to move every pixel. It'll accept a whole bunch of parameters. First, the position of the current pixel we're evaluating. Then the overall origin of the whole view. Then the text size we're changing. And then we'll make this thing store how strong the effect should be, how much tilt we want. And that's our function definition complete. The rest is all shader code. So when SwiftUI passes width and height to us for the shader, they'll be measured in screen space, 400 pixels wide by 200 pixels high, for example. We don't want that. We want relative positions and relative sizes between 0 and 1, where 0 means top or left, and 1 means bottom or right. These are often called UV coordinates. So we can start by converting our absolute values into UV coordinates. We need to figure out how much to move this current pixel. I'm just going to use strength for now. Move every pixel by the same amount. It's wrong, but it's a start. We'll store the movement amount in this Z variable. We then divide our x position by the movement amount, and then convert that back to screen coordinates. And this code is not correct, but it's a good starting point. Here's how it looks. As the slider comes down, the text is squeezed. To make it a little better, we're going to change the code. Now we'll move towards the center of our view before applying our movement amount. And then apply it, and then move back to original position afterwards. Now we'll squeeze the text towards the center rather than towards the left edge. Next, we want to fix this float z equals line. Just using the strength is not enough. It means every pixel is moved the same amount. Instead, we're going to multiply that by this pixel's y position. This means pixels near the bottom have more of the strength applied. And now we get a sort of rough perspective tilt effect. To make it better, we're going to invert the z value. So rather than writing this, we will take it away from 1. We're flipping it around. So now a value of 0 means no effect, and 1 means maximum effect. But we're also making the perspective go the other way. It's getting small at the bottom rather than small at the top. So to get the final effect we want, we're going to invert uv.y, which means going from this to this. And that's our final shader code. That's all of it. And here is the final result. A strength of 0 leaves the text natural, whereas strength 1 warps it a lot, getting smaller at the top. And with the same kind of logic, you can do so much more. Here, if we stretch rather than squeeze, we get this effect. And these are both examples of what we call distortion shaders. They let us stretch and pull SwiftUI views freely. You have complete control over the pixels. So we create this kind of water effect here and see how it looks with gentle movement like this, or get stronger movement like this, or go even higher. And this is still regular text. It still works great with things like voiceover and dynamic type. Another useful shader is called a color shader. We can recolor individual pixels to create a different effect. For example, this is a gray to white animating gradient. It's not a lot, but it might also seem familiar for the older folks in the room if we change a text from word art to something like slide to unlock. But why just stop with grayscale? For the true 90s feel, we want to bring in all the colors. And you might wonder, when would you want this? Well, obviously the answer is, when would you not want this? But you can also tone it down a little bit. For example, what if we took this text here and said, OK, let's blur it a little bit like that. And then maybe draw that blurred text more than once, say drawing it twice to pump up the colors. And then over that text, draw the original unmodified text as it was at first, creating that kind of effect. Now it's the kind of thing I clap in, yeah. So we have native SwiftUI text being passed through a custom renderer and then filtered through an animated metal shader. We're leveraging so much power here. I know it's for a slightly frivolous effect, but I hope it shows you how customizable the TextRenderer protocol actually is. We really have complete control over the way every piece of text, every line of text, and even every character of text is rendered. Now, I've shown you a whole bunch of code here, but hopefully giving you some good ideas too. If you're keen to try it out, I have some good news for you. I've taken all the code you've seen in this presentation and made a project out of it called Prismic. Prismic is a native macOS project that will serve as examples of all the code you've seen today for you to try out in an interactive environment. You can change things, add the blur, change the strength, whatever you want to. So that's Prismic. Best of all, as soon as I'm off stage, it'll be open source today for everyone to learn from and everyone to reuse on GitHub. Now, before I'm done, I want to add just two more things. First, you might wonder when you'd want to have this kind of thing in your projects. Well, you might be interested to know word art was invented by none other than Scott Forstall. He was an intern at Microsoft when he invented it. The next year, he left Microsoft to join Steve Jobs at Next, followed Jobs to Apple, and then led the team that created iOS originally. And the second thing I want to say is this. Please remember, with great power comes great responsibility. But with great rainbow text comes great eye strain. Thank you very much.